So in lecture on Thursday, this was one of the slides that I moved towards the end and we didn't work through. But in looking at the homework and some of the questions that have come in, I think it'd be a good idea to work through this problem together. So we have two types of reactions. We're going to have elementary reactions where we can get the rate law right from the reaction. And so in an elementary reaction, for example, say if I had something simple like A goes to B, and I just have 1 mole of A goes to 1 mole of B. And if this is an elementary reaction, the rate law then would simply be rate equals the rate constant times the concentration of A. That's a first order reaction. It's a first order reaction because I can use, as an elementary reaction, I can use the molar coefficients to tell me the order of the reaction. A second order reaction could look like A plus B goes to C, and the rate law for that, if this is an elementary reaction, would be rate equals the rate constant times the concentration of A to the first times the concentration of B to the first. Because again, I've got 1 mole of A reacting with 1 mole of B to make 1 mole of C. So that would be a first order reaction for A, first order with B, overall second order. Also, we could see a second order reaction that could look like this, like 2A goes to B. This would also be a second order reaction. If it's an elementary reaction, rate equals the rate constant times the concentration of A squared because of that coefficient of 2. So one type of reaction will be an elementary reaction where we can get the rate law right from the reaction and the stoichiometric coefficients. The second type of reaction, and this is more like real life, this is more like most of the reactions you're going to see, you will have to find the rate law from a data table much like this. And so how we want to find the rate law is basically we need to see when I change the concentration of one species in the reaction, what impact does that have on the rate of the reaction? And you'll notice that when you're doing this, you only want one concentration to change at a time. So we're going to check chlorine dioxide. We're going to triple that concentration between experiment 1 and 2. We're going to keep hydroxide concentration constant so that I only have one variable. That way I can say this change in concentration here is directly related to this observed change in rate. For our second set of experiments, now we want to figure out the rate of the reaction with respect to hydroxide. Now we want to use experiment 2 and 3 because there we're going to triple concentration of hydroxide and we're going to hold chlorine dioxide concentration constant. So when we look at those rate values, right, we can use these rate values to get us an idea, an understanding of what impact hydroxide has on the rate of the reaction. And to calculate this impact, the order of the reaction, I like to use this equation here, basically, concentration large over concentration small raised to the power of n equals my rate from the larger concentration divided by the rate of my smaller concentration. And if we take a look and we're going to pick first, I'll do experiment 1 and 2, right? So we're going to do chlorine dioxide first. So for chlorine dioxide, my largest concentration is 0.06. My smallest concentration is 0.02. That raised to the power of n, right? N is our reaction order. That is what we are looking for. That's what we need in our rate law. So 0.06 divided by 0.02 raised to the power of n equals, my larger rate is 0.0248 divided by my smaller rate, 0.00276. So just so you know, right, I'm using only experiment 1 and 2 here because I'm changing just this concentration. Hydroxide is staying the same in both of those experiments. Again, largest concentration has the fastest rate, smaller concentration, the smaller rate. So divide these two, I divide these two, and I'm going to end up with 3 to the n equals 9. So what is the order of this reaction for chlorine dioxide, right? Well, 3 raised to what power equals 9, right? 3 squared equals 9. So n equals 2 for chlorine dioxide. I want to do the same calculation for hydroxide now, except for now I'm going to use experiments 2 and 3. So for hydroxide, I've got 0.09 divided by 0.03 raised to what power equals, my larger concentration has the largest rate, 0.00828 divided by 0.00276. Divide those through, and I get 3 to the n equals 3. Right, so for hydroxide, 3 raised to what power equals 3, right? 3 raised to the first equals 3. So now I have the rate law of the reaction. The rate law of the reaction would be rate equals my rate constant times the concentration of chlorine dioxide squared, because that's what we found over here, times the concentration of hydroxide to the first power, because this is not an elementary reaction. So if you're given a data table like this of different concentrations and different rates, we are going to have to find the rate law for that reaction. The next question here, calculate the rate constant with proper units. All right, the rate constant is K. Often students think they don't have enough information to find the rate constant for a reaction, but we know the rate law. So all you need to do to find the rate constant is just pick one experiment. So let's just pick experiment 1. In experiment 1, we want to use all of those values to basically say, okay, I've got a rate of 0.0248 molar per second. That equals my rate constant that I don't know. When my concentration of chlorine dioxide is 0.06 molar squared, my concentration of hydroxide is 0.03 molar to the first. Square that, multiply those two together, and I get 0.0248 molar per second equals my rate constant times 1.08 times 10 to the minus 4 molar cubed. I want to get rate constant by itself, so I'm going to divide both sides by 1.08 times 10 to the minus 4. 1.08 times 10 to the minus 4. Right, that molarity cancels out. One of those cancels out. And I'm going to end up with a rate constant for this reaction of approximately 2.30 times 10 to the 2. This is a third order reaction. So for a third order reaction, our rate constant should be molarity, -2 seconds to the -1 for our units there. All right, but we can find that rate constant because we know two concentrations and the rate that corresponds to that concentration. So now that we know the rate law, we can find the rate constant. Now that we know the rate constant, we could actually find the concentration. We can find the rate, rather, at any concentration of these two reactants. Question 14 from the homework is similar to that, except for it's a little bit harder because you'll notice when we're trying to find what entries I need to use to find my change in rate for the reaction, the impact, the order of the reaction, we'll notice that, sure, for B, I could use entry 1 and 2 because the concentration of A does not change. However, for A, if I take a look at the concentrations of B, they are all different. So that makes it harder to find the rate of the reaction, the impact that A has on the reaction. But we can actually do that, and we'll work through that. But we'll start with B first. So for B, I want to use experiment, all right, if this is experiment 1, 2, and 3, I'm going to use experiment 1 and 2. So for the impact of B, I've got 0.3 divided by 0.1 raised to the n equals, my rate is 2.55 divided by 0.85. So I divide those through, and for B, I get 3 to the n equals 3. So n equals 1. So that's a first order reaction with respect to B. A first order reaction means if concentration doubles, the rate doubles. Or in this case, the concentration triples, the rate of the reaction triples. So we can use that to find out what the rate would be if we were to change the concentration of B. And we need that now to help us find the order of a reaction with respect to A. So for A, we want to use experiment 1 and experiment 3, but we have to do some changing first. So if we take a look at A, and I take a look at experiment 3, I've got 3.75 as my concentration of A. My concentration of B is 0.2, and my rate, when all of those things happen, my rate is 5.10 molar per second. So we know this is a first order reaction though with respect to B, which means if I cut the concentration of B in half, I want to keep A constant. But because it's first order, if I cut the concentration of B in half, that should cut the rate of the reaction in half. So I'm going to divide this by 2 as well, because I divided this by 2. So 5.1 comes out to be 2.55 molar per second. So now I can use experiment 1, 1.25, 0.1, and 0.85 to find the rate of the reaction, the order of the reaction with respect to A. So for A, right, my larger concentration, 3.75 divided by 1.25 to the n. Right, we want to use these two entries right here because the concentration of B stays the same. So 0.375 divided by 1.25 equals 2.55 divided by 0.850. We divide that through, and again, we're going to get 3 to the n equals 3. So again, this is a first order relationship with respect to A and B. So when we put that together, we're going to get a rate law for the reaction of rate equals the rate constant times the concentration of A to the first times the concentration of B to the first, which looks like choice C right there. So this question is a little bit harder than what I would give you on an exam because they're making you kind of work backwards and find what the rate would be. If this was an exam situation, I would give you a case where you have one of these that's constant and one of these that's constant. They did not do that to you here. They changed all of these, which made us go through this extra step to basically find B, use that information to say, okay, if this doubled, well, I cut this in half, the rate should also be cut in half because that's a first order relationship for B, and B has a first order relationship in this reaction. Question 15 is very similar in that they do the same thing where they change up the concentrations on you. So for 15, we want to use, first, I'm going to use the first two experiments to find A, and then we're going to use the information here in experiment 1 and 3 to find the impact on B. So first things first, I'm going to find the order of the reaction with respect to A. So my larger concentration, 0.2, my smaller concentration, 0.1, raised to the n equals my larger rate is 0.92, my smaller rate is 0.46. Divide that, I get 2 to the n equals 2. So this is a first order relationship with respect to A. So that means I can come down here and then use this information in A. So between here and here, I triple A. So when I've got experiment 3 is 0.3, 1.25, and 1.38. That's the concentration of A, concentration of B, and that's the rate of the reaction. I know this reaction is first order with respect to A, so that means if I double it, I'm doubling rate. Or if I triple it, right, I would triple the rate of the reaction. So I'm going to drop this down to 0.1 because I'm going to basically divide this by 3. I want to keep this the same because that's my variable, right? Between 1 and 3, I got to change that concentration. And if I divide the concentration by 3, I need to divide the rate by 3. So I divide this by 3, and my new rate of the reaction is 0.46. So now I can use experiment 1 and experiment 3, the modified version of experiment 3, to find the order of reaction for B. So for B, right, larger concentration, 2.5, smaller concentration, 1.25, raised to the n equals 0.46 is that concentration, or my rate, and then my other rate is also 0.46, which is kind of an interesting thing, and we'll see in a minute why that happens. So I get 2 to the n equals 1. Right, 2 raised to what power equals 1? 2 raised to the 0 equals 1. So this is a zero order reaction with respect to B, and we can see that because zero order tells you that B has no impact on the rate of the reaction. So that means if I double the concentration, rate stays the same because there's no impact on the concentration of B and the rate of the reaction. I could put tenfold, right? 10 times as much B in the reaction, and again, the rate should not change because it's zero order. So we finished step 1. We've figured out the rate law for the reaction. The rate law for the reaction equals the rate constant times the concentration of A to the first. B does not show up in the rate law of the reaction because B is zero order. It does not impact the rate of the reaction. So that means when we're calculating rate, we should not include the concentration of B because it does not impact the rate of the reaction. Now we can find the rate constant. To do that, we're going to take our rate law and we're just going to pick one experiment. So I pick experiment 1. All right, I'm going to take my rate law, rate equals the rate constant times concentration of A to the first. Well, my rate is 0.46 molar per second. I don't know the rate constant of the reaction, and I have that when my concentration of A is 0.1 molar to the first. So I get 0.460 molar per second equals K times 0.1. Divide by 0.1. Molarity cancels out, and we're going to get 4.6 inverse seconds as our rate constant for this reaction. So that gives us, right, choice A for question 15. Again, just like question 14, this is a little bit more tricky than what I would give in an exam situation, because I would give you a fourth entry where one of these was kept constant and one of these was kept constant. For question 18, this is a standard question. You'd expect to see something like this on an exam. How long will it take the concentration of A to decrease from 0.5 molar to 0.2 molar in a first order reaction where the rate constant is 0.800 inverse seconds? Some key information they give you, right, is that this is a first order reaction. So for a first order reaction, natural log of concentration at time t equals negative kT plus natural log of concentration at time 0. Because it's a first order reaction, we need to use the integrated rate law for a first order reaction. They tell us the concentrations. So AT is at some point in the future, A0 is our initial concentration, and our rate constant is 0.8. So we can plug in. So the natural log of 0.2 equals negative 0.8 inverse seconds time. We're looking for time, plus the natural log of my initial concentration, which was 0.5. Take the natural log, and I get negative 1.609 equals a negative 0.8 inverse seconds times time, plus the natural log of 0.5 is a negative 0.693. We're going to add that across because we want to get t by itself, so we add this 0.693. And I get a negative 0.916 equals a negative 0.800 inverse seconds times time. We divide, because we want to get time by itself, we're going to divide by 0.8. Divide by 0.8, and negative 0.8. And for time, we should get something like 1.15 seconds. The biggest thing with these equations or these questions is just knowing what equation to use. And they told us that when they said this is a first order reaction. First order reaction means we want to use natural log of concentration equals negative kT plus natural log of our initial concentration. From there, you want to make sure you're plugging in the correct concentrations in the correct places in that equation, and then solving for rate constant or concentration, or in this case, time. Question 22. This has to do a little bit about the rate determining step material that we talked about on Thursday. So consider the proposed mechanism for the decomposition of hydrogen peroxide going to water and oxygen in the presence of iodine. What is the rate law for this reaction? And when we talked about rate determining steps, right, we said that the rate determining step, if you've got a multi-step reaction, the rate determining step is going to have the highest activation energy for that reaction. And so if we look at something like this, where the first step is the slow step, that's got the largest activation energy. And then our second step is going to be faster because it's got a lower activation energy. So there's number one, there's step number two. Right, so we look at this reaction that they give us. They tell us that step one is the slow step of the reaction. That's what's going to set the rate of the reaction. And in the first step, we have one hydrogen peroxide and one iodine. because the second step is the fast step, that's not going to set the rate of the reaction, right? The rate determining step sets the rate of the reaction. And in the rate determining step, we only have one hydrogen peroxide and one iodine. They don't give us any rate data and concentration, so we can assume this is an elementary reaction. So we can assume that we can get the rate law, rate from the reaction, to say rate equals my rate constant times the concentration of hydrogen peroxide times the concentration of iodine, because I've got 1 mole of hydrogen peroxide in the reaction reacting with 1 mole of iodine. And that would give us rate law of C. Again, we can only do that because this is the slow step of the reaction. This is the rate determining step. So all that takes place in this step of the reaction is what determines the rate of the reaction, because the second step is so much faster, right? This is the bottleneck. This is what sets the overall pace or rate of the reaction. This second step is so much faster that it has no impact relative to the first step on the rate of the reaction. So we can go and see what's in that reaction to get the rate law of that corresponding reaction.